All right, hello everybody. I'm meteorologist Jeremy Wheeler, and we are going to have some fun today with pressure, and we're going to have a whole conversation about pressure. The whole day is going to be about pressure, and I am under pressure to do a good job here. I am meteorologist Jeremy Wheeler, and we've had a couple of successful podcasts so far. So thank you, appreciate it. Yeah, your support, and we're going to try and do a third round here, and I think we're going to have a good time. So let's talk about what's going on today. And again, it is pressure, and we're going to do a few things. Let me go back to myself really quickly. We're going to talk about the pressure, the history of it. We're going to talk about what measures it, some of the tools that we use, and then we're going to talk about it in the atmosphere and talk about, how it relates to us, and physically, how it relates to us, and weather maps. We're going to take a look at some weather maps, and we'll talk about some active things as well. Okay, so let's go back to that Mac's computer, and let's get started on the lecture. And so the pressure, what is it, right? It's a simple question. So the simple answer is, how much push there is on a surface, right? So we push on a surface. If I was to push on this desk that's, by me, there's a certain pressure there. If I were to press on a window, right, there's a pressure there. So it's how much push is on that surface. So that's the basic. Now, how about the scientific definition? And so scientific is the amount of force per unit area. Ooh, boy, that's getting a little technical. So let's break it down. So amount of force, right? That's just simple. We talked about it. Force is technically mass times acceleration. So if I put my mass in my hand and I push on it, there's an acceleration. And it's, the area is my hand. So that's pushing on it, right? And so there's amount of force per unit area is, the amount of push on a certain amount of space. And so if you've got a big force and a big area, well, that might equal out. It's a big, it's a lot of pressure. But if I've got a small force on a big space, well, that might not be too much pressure. So, wow, that balloon has a hole in it. Experiment failed. Okay, so we've got a balloon here. And I'm going to apply some force, some pressure on it a little bit, and we're going to see what happens. So I'm going to just wait a minute. This is let's do this. There we go. Let's try this. A little bit of a close up. So we're trying pop this balloon. So there's a good amount of pressure, right? The size of my hand is the area. And so I didn't pop the balloon though, right? I did push on it. I was being a little dramatic. But now we have a pin, a safety pin. And the small area there, if I were to put the same amount of force on this, then, it's going to pop it. Wow, that freaked me out even. Okay, so we applied a high amount of pressure by using the pin. We used a force on a small area, and so that pressure was huge. So let's go back to that. Okay, so we got now kind of what pressure is. How do we measure it? Well, the word, barometer, which is how we measure it, comes from Greek, baros meaning weight and meter meaning pressure. Yasu. Liquid or metal expands or contracts with varying pressure, and you've got the on the right there the picture of the barometer. It's a mercury one, so it's the height of the mercury going up or down. And it's measured in a whole bunch of different units. There's the bar, there's millibars, which is kind of what we use all the time for in weather, and then the atmosphere, believe it or not, and pounds per square inch. That one's pretty common. All right, so the history of the barometer. Who invented it? Well, Evangelista Torricelli, 1644, invented it and used mercury in a tube. He had some influence from Galileo, believe it or not, which we talk about that on these shows quite a bit. Galileo was one smart hombre, and he knew a lot. So Torricelli was also a smart scientist, but he had some influence. So that was the kind of the father of it. Aneroid barometer is a metal capsule in which a partial vacuum is produced. And so, that's kind of one of the more common ones that we use nowadays. We don't use mercury too much. They don't use mercury in a lot of things nowadays just because of the danger of it and the toxicity of it. We talked about that with when it came to thermometers. And the classical aneroid barometer was affected by Lucian Vitti in the 1840s. Also invented the barograph, which records pressure. So that is shown right here, courtesy of NOAA. And on that one, it's basically you've got a thing that takes notes, right? It rotates around, the column rotates around, and now they're digital. I mean, they have paper ones, but now they're digital. So it records it, and so it takes that needle and records it once that drum rotates around, and so you can measure the pressure, and that's really valuable, especially when you have big storms like hurricanes and things coming and affecting things. So you want to try and measure that pressure through time and get what's called the tendency of that. So it's a good tool. All right, so let's go take a look at the next thing. Now there's the history of the barometer. So now they have electrical barometers in phones, and so these are using very tiny mechanical devices, electrical parts to be able to measure that. I thought it was something called piezoelectric, but I found out that it wasn't through just a whole bunch of different sources. But piezoelectric effect, that basically is sometimes crystals. When you press them, they put out a certain voltage, a certain specific material, and so you can get electrical charge and measure that. But these phones now actually have, and other devices have little electrical mechanical device in there, micro sized, of course. And so this is one of them. This is an electronic barometer, and it will measure that. So these are some of the tools that we use. And so you may think, well, what are we measuring exactly? Well, what is the pressure? Well, the pressure, if you think about a column of air, it has mass, right? So there's a column of air there, a giant one that's miles high, and so in that there's air, and that air has mass and it weighs, and so that presses down on us, and that's the force that we feel, the force on our heads and around our bodies. So sometimes you have areas of high pressure, sometimes you have areas of low pressure, but that weight of that column is pressing down on us and producing that pressure, and that's what we're measuring when it comes to the barometer. So it's a very important tool. All right, so what we did was we just talked about kind of what pressure is and how it's measured. Coming up in a little bit, we'll talk about some examples I'll show you a couple of devices, and we're going to also take a look at some examples in the real world. All right. All right, welcome back. And so we just talked about, what pressure is. We talked about, what measures it, things like that. And so now we want to try and get some real world examples and, what goes on. So first things first, I'm going to show you an example of an open end barometer. So let me grab it here really quickly. And so this is an open end barometer. It looks like a swan. It's a ball barometer, and it's got the blue liquid in there. So what happens is this is open ended, meaning that this is open on the top. And if you see my blue hand here, it's because this leaked out a little in transport, but just a little bit. So it's just food coloring though, so it comes off. But when the pressure outside increases, the pressure will be on right up through the mouth, right down the neck, right into the body. So it's water, will go up inside and will go down out here. And then when the pressure drops, let's say we have a big thunderstorm or a tornado or something like that, then this will start to come back up the neck, and it will actually leak out. If there's a big bad storm like a hurricane, the pressure will drop outside, so the pressure inside will be relatively stronger, and it will actually push out and it will come out. So this is the ball barometer, and this was Johann Wolfgang von Goethe. He lived in the late 1700s, early 1800s, and so he developed this using principles from Torricelli. Now here's another one that we have. Swan down. You have to sweat the swan down. This one is this is a barometer. This is the old-fashioned type, right? I got this from a thrift store. So this is an aneroid barometer. On the back, you can see a way to manipulate a little bit. I think the recorder, the little golden part is recorder. But bottom line is this goes up or down depending on the pressure. So this is my barometer, and it measures the pressure through an aneroid. And then we've got a thermometer on top, and it's got a hygrometer on the bottom, which we're not talking about today. I don't know if this is directly attached to it, the top part. I don't know if that's the actual aneroid or not. I'm not sure. It's not the thermometer, I know that, but it might be. Looks like it could be, and then it's measured maybe through a tube or something. So that's, really cool stuff. Again, this is the old-fashioned, good old aneroid barometer, and the farmers, you can see the word change and rain and fair, and so, kind of depending on where it lands on there, they kind of knew, whether or not some bad weather was coming. All right, so let's take a look at this. This is some neat stuff here. This is the record pressure, the highest pressure recorded, 1,083 millibars. That's MB millibars, Agata, Siberia. I don't know if I'm pronouncing that right. I apologize. December 31st, 1968. Just for reference, the pressure, the normal pressure usually is about 1,000 millibars. So that's 1,083 millibars. That's huge. That's strong high pressure. Probably a big area high pressure in cold, temperatures, something like that. So some huge cold outbreak, in Siberia. And then the lowest pressure recorded 870 millibars, Typhoon Tip. October 12th, 1979. That was one of the biggest, strongest typhoons on record, which, it's in another part of the world, it's basically a hurricane. And so that one was the lowest. And the lowest Atlantic hurricane, Wilma, 2005, 882 millibars. So again, remember, hurricanes and tornadoes are extreme areas of lower pressure. So these are some of the lowest pressures that you have. Meanwhile, that high pressure usually get happy weather and sunshine, which we'll talk about in the next weather segment. Yeah. Anyway, let's take a look at this next example. So here's the tire. This is a bike tire. And so, we talked about air pressure outside, but in a bike tire, you talk about, the pressure on the inside. And so this is just a simple bike tire. And we got about 20 to 130, up to 100. I'm surprised about that when I read that. 130 pounds per square inch. That's a lot of pressure. I think maybe some of the professional bike riders pump them up big time and make them like concrete because most of them, the smaller ones, are like 20 to about 30 or 40 at the most. So I don't know. But anyway, then that's a bike tire. And then you've got a car tire, which is about 30 to 35 PSI, and that varies a little bit. A truck is about 80 to 100 PSI, pounds per square inch. Right, pounds per square inch. Are you gonna do accents all day? I mean, what are you gonna? What was that? Well, actually, that's back in the day. There's a Simpsons episode, and there was a cream puff, and they had a whole bunch of butter, and he said, 25 pounds of butter per square inch, and it just always sticks in my head, so that kind of leaked out a little bit. So I apologize. Yeah. All right. So anyway, let's take a look at the max here. And so what we're going to do is I'm going to show you an example of pumping it up. And so I pumped up this tire here. And so the audio is not playing, but I'll just tell you, this is a compressor. It presses all the air into it, and then it shoots it out, and that's what fills up the tire. I was trying to think of something funny that I was actually not saying, kind of like Mystery Science Theater 2000 or 3000, and something like, let's start it over again. Hey, everybody, guess what? If you pay me $50, I'm going to blow up this tire with air right through this compressor. No, I didn't really do that, but that's just kind of fun. So again, and this is the compressor. This is what it looks like up close. And so I needed to pump up my tire. And so you put in how much pressure you want, pounds per square inch. And I think I needed 35 for that particular tire. And that tells you on the inside, what size tire or what pressure it should be. And so I did that. And yep, that's right. I could actually pump up my own tire through my own compressor. Now they're pretty handy. You can actually plug them in. You can plug them into an outlet, but you can also usually plug them into what's the old cigarette lighters, which now not too many people, as many people smoke, but still people use them for the USB ports or to charge up your phones, right? That's where you plug in your charger. So that's where you can plug those in. If you're on the go, let's say you get a tire, it's losing pressure, maybe you got a small flat, then you can go out there and do that. You fix your tire right there. And then, of course, they have the cans now that you can actually, it's got a little bit of sealant in it. So you put that on your tire and it actually pumps up your tire and a little bit. It puts a little bit of air in there, but not much. But it also puts that sealant in. So the sealant hopefully goes to the hole and then, fixes it. So that's one way that you can try and fix that. And then, of course, you have compressors, at gas stations. You go there and you can fill up your tire and, you can fill it up that way. That's preferred because that's got a lot more pressure. But then again, sometimes you can't make it to the what do you call it, the gas station. So you use that. All right, so we're going to take another break. And when we come back, we're going to talk about pressure in nature. All right. All right, everybody, welcome back. And so we just talked about, some examples of pressure. And now we're going to talk about it in the atmosphere. So I do want to talk about this, a balloon, right? We'll go back to a balloon. So what's really happening here? So I'm forcing the pressure in my lungs, higher pressure. I'm forcing the pressure into this balloon. Now the pressure in balloon is more than the atmosphere, the outer atmosphere. So I'm holding it, all right? I'm holding it. I swear, I'm holding it. And so then now we're going to let the... I had to. All right. So anyway, let's get serious now. So we're gonna let it out, and so what's happening is the pressure in the balloon is pressing that air out, and now it's normalizing, and the pressure it's equalizing, right? So the pressure inside the balloon right now, there's hardly any, but is equal to the pressure outside the balloon in the atmosphere. So that's the wrong button. Now let's take a look at some things on the Mac's computer. And we talked about that. So now here's the atmosphere. We're going to load it up. And this is the pressure with height. The pressure decreases with height. And so on the right, you have all the different heights in meters and feet. And so you can see, about the level that planes fly. And so on the left-hand side, you can see some numbers. At the surface, I know it's kind of cut off there, but 1,000 is the surface. The WAVY Science Lab logo cuts it off there. But as you go up in height, you've got 850 millibars, at about 1,500 meters. I think that's a little different, but that's an average, I guess. And then you get up around 300 millibars. That's about where the jet stream is. So that 300 number on the left is 30,000 on the right. And so, that's a lower pressure. Remember, the pressure at the surface was 1,000. So up high, you got 300. So the pressure is much lower, and then you get up close to the edges, the top there, and you got 100 millibars. Then you go, the atmosphere can go up much, much higher than that, and where you have, down to a couple of bars of pressure. So pressure decreases with height. So we think about those columns of air, and so some, warm and cool air rather, determines the height of those columns that we talked about, a column of air weighing down on us. So there's a different density. So what happens is that the red one is higher than the blue one. So the air wants to not only, it does press down maybe, but it also kind of spreads out. And so it wants to go from red to blue on the top. And that's how the jet stream is formed, basically. The air wants to go from that area of higher pressure to lower pressure. And so that's how the jet stream happens. And then you also have areas of relative high and low pressure. So on the left, we got an area of low pressure. On the right, there's an area of high pressure. In low pressure, air tends to rise, right? It goes up. And so then on the left, or the right side rather, you've got high pressure and air sinks. So high pressure gives you happy weather and sunshine. Low pressure gives you rain showers, thunderstorms. And so in this case, high pressure was over the Bermuda. There's a Bermuda high, and there was an area of low pressure down coming off of Africa, and that was moving west. So we had these lines of equal pressure, and that's called a brain fart. I will think isobar. Thank you very much. Ah, yes. Isobar. I knew it had it in me. All right, so isobars. So you have these areas of low pressure. These hurricanes are extreme areas of low pressure. And so this is a hurricane. Air wants to go into it, right? It wants to go towards it, but it spins because the Coriolis force is out there. The Earth spins, so the air spins, and that's a whole different lecture. But the bottom line is the air doesn't go straight into the middle. It starts spinning. And so it spins into what's called the eye, and then that forms. Now, that is a hurricane, extreme area low pressure. Then you get some major winds around it, winds of 100 miles an hour, sometimes 150 miles an hour, and around that core. So that's a big system. I mean, these things are bigger than several states sometimes. So the smaller version, it's not a version even, but this is a tornado. A tornado is an extreme area of low pressure. It creates a vacuum. And so when you have that, you got that vacuum, the air wants to go in to the tornado. It just spins. There's no eye per se. Some have said there's an eye, so that's maybe arguable. I think maybe in the biggest ones there's a little bit, but most of the time, I mean, it's got a core that's just kind of spinning around itself. And so that is the tornado. It's an extreme area of low pressure. And so, these tornadoes, the winds can get up to 100, 200, 300 miles per hour. It can get very strong, and that's damaging when you get a wind of 300 miles per hour. So we try and track these. They can do major damage even on the low end. Even on the low end, we have winds about 70, 80 miles an hour. That can do some damage, but usually they're about 100 to 120 miles an hour in a lot of these things. And so it can damage homes, it can rip up trees, it can throw cars. And tornadoes, again, that's that area of extreme low pressure. So we track these and try and keep people safe. And if there's a tornado out there, we can actually look at it on a radar. We talked about that, behind the scenes. A radar shoots a beam of energy out and bounces off of the liquid water around a tornado in the storm, and it can tell us information. And so we use the Doppler effect. You can actually tell. The spin, the amount of spin and the amount of speed. One side's going towards and one's going away. And look at my blue fingers. Oh, my blue fingers. So that's how we determine if there's a tornado. So again, pressure affects everybody. Some people get pain if there's pressure, and they'll actually feel that. If like an area of low pressure is coming, a storm's coming, they can feel it. Hey, I got a storm coming. They can actually feel that, so they can tell you about it. All right, so one more thing before we go. We're going to take a look at the environmental tip of the day. And so, you've got food out there, and people throw a lot of food away, a lot of things they shouldn't throw away. But the USDA said 133 billion pounds of food were wasted in the U.S. in 2010. So you can compost. You can use eggshells, banana peels, coffee grounds, old fruit. Put it in a jar, probably an air sealed jar, and then you can actually put it out in your lawn, and that will help. All right, so that's it for today. Again, I'm meteorologist Jeremy Wheeler, and it's been fun. We're going to be back next week with another topic, another lecture, and hopefully learn a few things and have some fun. Everybody have a great day, and thanks for joining me here on WAVY Science Lab.